Hello everyone. In this video, we'll look at another application of Bayes' theorem to a problem similar to, but older than, the Monty Hall problem. If you haven't looked at the video about applying Bayes' theorem to the Monty Hall problem, you might want to watch that one first. The problem we're going to be looking at was first formulated by the French mathematician Joseph Bertrand. It's known as Bertrand's box paradox. It has a very similar logical structure to the problem, to the Monty Hall problem, and it has a similar paradoxical feel to it. In Bertrand's box paradox, there are three boxes, each with two drawers. Each drawer contains a coin. One of the boxes has two gold coins. It has one in each drawer. Another box has a gold coin and a silver coin. And another box has two silver coins. So the question is, if you open a random drawer of a random box and take out a gold coin, what's the probability that that's the box that contains two gold coins? Let's suppose you open a drawer in box A and you find that it contains a gold coin. What's the probability that box A is the one that contains two gold coins? For now, let's use some abbreviations. We're going to let AGG stand for the statement, box A contains two gold coins. And we're going to let ARG stand for the statement, a random coin drawn from box A is gold. The first statement will be our hypothesis, and the second statement will be our evidence. Before we take a look at Bayes' theorem, let's take a look at the sort of intuitive reaction to this question. Intuitively, if you were to open a drawer in box A and find that it contains a gold coin, then you can rule out that box A is the one that contains two silver coins. Box A then must be the one that has two gold coins, or the one that has one gold and one silver coin. And it feels like it could be either one, and the odds are evenly split. So the intuitive answer is that if you draw a random coin from box A and it's gold, there's a 50% chance that box A is the one that contains two gold coins. Let's check that intuition using Bayes' theorem. Here I have plugged in our abbreviations for our hypothesis and evidence into the simplified form of Bayes' theorem. So this reads, the probability that box A is the one that contains two gold coins, given that a random coin drawn from box A was gold, equals the prior probability that A is the one with two gold coins, times the probability that a random coin drawn from A will be gold, given that A is the one with two gold coins, divided by the total probability that a random coin drawn from A is gold. So these are the probabilities that belong on the right-hand side of the equation. We see that the prior probability of the hypothesis that A is the one with two gold coins is 1/3. Why is that? Because prior to opening a drawer in box A, we know that one of these boxes has two gold coins, one of them has a gold and a silver coin, and one of them has two silver coins. So before any box has been opened, any drawer has been opened, A has a 1/3 chance of being the box that has two gold coins. Let's look at this term on the upper right, the probability of the evidence given the hypothesis. So if we assume that A is the one with 2 gold coins, what's the probability that a random coin drawn from box A will be gold? The answer is it's a 100% chance. If A is our box that has 2 gold coins, then we will necessarily find a gold coin when we open one of its boxes. So it's a 100% probability. Let's look at the total probability of the evidence. The probability that a random coin drawn from box A will be gold. If you look back 2 slides, you'll see that of all of the boxes, there are 6 drawers, and that means a coin in each drawer. There are 6 coins. Half of those coins are gold, half of them are silver. So the total probability of drawing a gold coin at random out of any one of these drawers is actually 1/2. So our prior probability of our hypothesis is 1/3. The probability of the evidence given the hypothesis is 100%. And the total probability of the evidence is 1/2. 1/3 times 1 is just 1/3. Divided by half means multiplying by the inverse, 2/1. And then the posterior probability will be 2/3. So the prior probability that box A contains 2 gold coins is 1/3. But the posterior probability that A contains 2 gold coins is 2/3. And this is at odds with the intuition that it should be simply 50%.